Myself, Dr. Anand Tirthabigudi, Professor and Coordinator, PG Studies, Department of Electronics and Communication Engineering, Global Academy of Technology, Bangalore 98. In digital electronics, today's session contents are Boolean algebra, 3 basic binary operations, special cases of binary operations, identities of Boolean algebra, De Morgan's theorem or law, proof for few Boolean algebra theorem, and finally we are going to discuss logic gates. Boolean algebra. Boolean algebra is a system of mathematical logic developed by George Boole. The laws of Boolean algebra are used to simplify and evaluate logic expressions. Operations like addition, subtraction, multiplication and division are used to evaluate arithmetic expression. Logic expressions have their own operations, that is and represented with a dot, or represented with a plus sign, and not is represented with a simple bar type of structure or a colon. Boolean contents. Boolean contents are 0, that is usually we are going to use for false statements, and 1 for true statements. Boolean variables. These variables can only take the value 0 or 1. Boolean functions. Each of the logic functions such as and, or, and not are represented by its symbols. Boolean theorems. The Boolean algebra has got its own theorems like identities and laws. 3 basic binary operations are firstly NAND operation, that is multiplication operation, and symbolically that operation is represented with a dot. For example, y is equal to a and b can be rewritten as a dot b. Its truth table is given below, and it indicates a is one variable and b is another variable, and the multiplication value as a result y is indicated as a dot b. Now for example, a variable value is equal to 0 and b variable value is also equal to 0. With simple mathematical function we can say a into b is equal to 0, and if a value is 0 and b variable value is 1, under that condition also the y value becomes 0 into 1 is equal to 0. And the third one, when a is equal to 1 and b variable value is equal to 0, under that condition the output y can be once again 1 into 0, that is equal to 0. Then the last case, when both the variable values, that is a is equal to 1 and b is equal to 1, under that condition y is equal to 1 into 1, that is the result is 1. And the secondly, the OR function, that is addition operation. The symbolic representation of OR gate has been done with the notation plus sign. Now y is equal to a or b, that is a plus b. With truth table it is possible for us to explain like a and b are considered as variables and the output y is considered as a plus b. When both the variable value a and b are equal to 0, then y is equal to 0 plus 0 is equal to 0. Then a variable value is 1 and b variable value is 0. Under that condition y can be represented as 1 plus 0, that is equal to 1. And another case, if A is equal to 0 and B is equal to 1, under that condition y can be still represented as 0 plus 1 is equal to 1. If both the variable values are high, that is 1 and 1, then automatically y is equal to 1 plus 1. In Boolean algebra, 1 plus 1 can be denoted as 1 only. Therefore, the y of A or B can be explained with this kind of truth table. And the third one is not operation. Usually this not operation we are going to call complement operation, and symbolically it is represented as super with one small slight line notation, and or we are going to write a bar over the variable. So now such operation is represented as y is equal to A complement. This is also A complement, another way of notation. So now truth table of NOT gate, if you want to see, then automatically we are going to say this NOT operation is, if A variable value is equal to 0, then complement of that A can be written as 1, and A variable value is equal to 1. Under that condition, the complement value of A is represented as 0. Now some special cases of binary operations. So here first operation can be explained like this: A dot B, it is nothing but A into B, where A is a variable and in place of B we have given a 0. It is already fixed, that value is fixed. So A dot 0 can be occupy only the 0, because already 0 is either A may be having the value 1 or A may be having the value 0. It doesn't matter, because whatever the 1 is there multiplied by 0 or 0 multiplied by 0 becomes equal to 0. Hence A dot 0 is represented as 0. Once again the next one, A dot 1 is equal to 1. Here A value may be equal to 0. So when A value is equal to 0, 0 dot 1 is equal to 0. That A value is retained as a result. Similarly, if A becomes 1 and then 1 dot 1 is equal to 1, that 1 is nothing but once again the value A what we have assigned. So therefore A dot 1 can be equated to A only. The next operation is A dot A. Either if A is assumed as 1, here also the same thing we should have to take. Therefore 1 dot 1 is equal to 1, that is the A value only. Once again it is A value may be a 0. Similarly here also we should have to put a 0. 0 dot 0 is equal to 0 only. Hence A dot A can be once again written as A only. So A dot or A multiply with the complement value of A. So in this special case what we can say here is A is going to attain the value 1, then automatically complement value of that 1 is equal to 0. Hence either the A may be equal to 0 or the assigned value A may be equal to 1. Under that condition the complement value may also changing to, if A is 1 then my complement value becomes 0, and A is equal to 0 complement value becomes 1. So whatever the value assigned for A, automatically what happens, one value out of these two is going to occupy the value 0. Hence A dot A complement value is always considered as equal to 0. Next, A plus 0 is always equal to A, because A is equal to 0, 0 plus 0 is going to become 0, and 1 plus 0 is going to become 1. Under that condition whatever the value you are going to assign for A, that value is reflected as the result of A plus 0. And the next case, A plus 1, irrespective of the value A, okay, here it is 1 is there. So A may be equal to 0 or A may be equal to 1, that doesn't matter, because 1 plus 1 is also equal to 1, 0 plus 1 is also equal to 1. Hence the we are, if anywhere, if we are going to say variable plus 1 is equal to the 1 only. So now the another case, A plus A is equal to A. How we have observed here A into A is equal to A, here also we are going to say A plus A is also equal to A, because A is equal to 0, both the cases we are going to get 0, 0 plus 0 is 0 only, hence the assigned value we are going to get as a result. If A is equal to 1 plus a is equal to 1, then 1 plus 1 is also equal to a, that is equal to 1. Hence a plus a is always equal to 1. Then the last case in this is a plus a complement. So already in the NOT operation, this AND operation, we have seen a dot a bar is equal to 0. Similarly in OR operation, like a plus a bar is equal to 1. So either a is equal to 1, then complement a bar becomes 0. So 1 plus 0. If this is going to become 0, first a is going to become 0, then the complement value becomes 1. So either a is going to occupy the value 0 or a is going to have the value 1. The output value of this equation remains 1. Hence a plus a bar is always treated as 1 only. Then a double complement, a complement of a complement, then automatically once a is complemented, the value of a is going to be inverted. Once again it is going to take the inversion, then automatically it is come back to the value a. Hence a double complement can also be taken as a only. So now the identities of Boolean algebra. Here different identities are shown, and is all these things are discussed with respect to AND forum. So there the identity law 1 dot a is also equal to a, because whatever the value a we are going to assign, that value is going to be reflected as a. And null law, that is 0 dot a or 0 multiplied by a is also equal to 0, because irrespective of the value a, the multiplication value is already fixed, it is 0. Hence 0 dot a is going to become 0. Idempotent law, it is a dot a, irrespective of the value, the whatever we are going to assign either 1 or 0. So 0 into 0 is 0, it is a value only, and 1 into 1 it is 1, that is a value only. Hence a dot a is equal to 1. Inverse law, that is a dot a complement is equal to 0. Whatever the value we are going to assign to a, once again the multiplication value is a complement of that value. Hence either if you are going to assign a is equal to 0, complement value even though it is 1, since the multiplication is there, hence the result is equal to 0. It is same in reverse this one also. If a is equal to 0 and a bar is equal to 1, under that condition also multiplication value becomes 0. Commutative law, this is a dot b can also be written as b dot a. So even though we are going to change the order of variable, okay, and then between that if you are going to put the dot, then the value of the equation is unaltered. That is the commutative law. Associative law, it deals like this: a dot b is taken as a one complete function, and that multiplication value is once again multiplied by with c. So this equation can be rewritten as a dot b dot c. So b dot c is made one function, and that function value or the product value or the multiplication value, if you are going to multiply by with a, the whatever the LHS value, we are going to get the same as RHS. Hence the equation value is not altered. That is going to be explained by the associative law. And the distributive law, a plus bc can also be splitted like a plus b dot a plus c. So even though if you are going to split like this, ultimately the value of the equation is not going to alter. RHS always looks to be equal with the LHS. Hence the last one is the absorption law, that is a dot a plus b. So here, so irrespective of the value b, whether it is going to 0 or it is going to be 1, then the value a what we are going to assign, that value is going to remain as the result of a dot a plus b. Same thing if we are going to deal with the OR form. So identity law can be expressed with the OR form 0 plus a is equal to a, and null law can also be represented as 1 plus a is equal to 1, because irrespective of the value of a assigned 0 or 1, since already 1 is fixed, we are going to get the answer as 1 when 1 plus a is considered. So idempotent law, it is a plus a, okay, whatever the value we are going to assign to a, that is represented as the result, because a plus a is 1 plus 1 is also equal to 1, 0 plus 0 is also equal to 0. Or next, the inverse law. So inverse law is 1 plus 0 means a value is equal to 1 and plus 0 we are going to get 1 as a result. So whatever the value we are going to assign to a, either 0 or 1, the result is not going to be altered and the result is always remains as 1. Commutative law, a plus b can also be rewritten as b plus a. Just by interchanging the variables at right side, the equation value is unaltered. Associative law, so a plus b plus c can be made into a plus within the bracket b plus c. Even though you are going to change the order, the result of LHS equal to RHS remains same. So distributive law, a dot b plus c is equal to a dot b plus a dot c. That can be distributed like, okay, a dot b plus c can be rewritten as a dot b plus a dot c. Even though you are going to split like this and you are going to write with the variable assigned values the RHS value, and looks like it is equal to LHS value. So absorption law, a plus b dot a is equal to a. So here whatever the value we are going to assign, because whatever the value b here we are going to assign, it is not going to come into account, and only in this equation a value is going to be highlighted. That's why a plus a dot b can be considered as a. Next we move to De Morgan's theorem or law. Here we are going to write two equations, particularly a plus b is equal to a bar dot b bar, and a dot complement or a dot bar is equal to a bar plus b bar. So finally the De Morgan's theorem is going to be written, and it gives an idea about these two equations. De Morgan's theorem states that the inversion bar of an expression may be broken at any point, and the operation at that point is replaced by its opposite, that is and is replaced by or vice versa. So truth table to prove De Morgan's theorem we can write like this. So take the two variables represented in the equation a and b, where in the first case a and b both the variable values are 0 0 and a is 0 and here b is 1, and next row it is a is assigned as 1 and b is assigned as 0. In the last row both a and b values are equal. So next complement of a, if you are going to take from here 0 is there, complement of a is equal to 1, here also 0 is there, complement of a is equal to 1, and 1 is here, complement of 1 is equal to 0, and 1 complement is 0. Similarly b complement value for 0 is 1 and 1 is 0, for b value 0 is complement is 1, and b value if it is 1, complement of b is equal to 0. Then the first equation, part of the equation or LHS, what we are going to see in this theorem is a plus b whole bar. So that we have written here. Then a plus b means 0 plus 0, the value is equal to 0, complement of 0 is treated as 1. Similarly here 0 plus 1 is equal to 1, and that complement value what we are going to write, a plus b complement is equal to 0. Similarly 1 plus 0 in the third row, 1 plus 0 is 1, but complement value of that becomes once again 0. 1 plus 1, even though that becomes 1, since complement is there, hence the value is going to become 0. Similarly if we are going to take the right part of the equation with the same variable, here a bar dot b bar is there. So now we should have to consider these two columns and respective row values. So if a bar is equal to 1 and b bar is equal to 1, then automatically 1 dot means multiplication with 1 is going to attain the value 1, and here the a bar value is 1 but b bar value is 0, hence the multiplication value is going to be 0. Similarly a complement value is 0 and b complement value is 1, either these two any one is 0, hence immediately we can come to the conclusion the multiplication value is going to become 0. So therefore the last row, if you are going to observe here, both the complement values of A and B are 0 0, hence complement values multiplication, that is 0 into 0, is going to become 0. This kind of verification is also termed as perfect induction method. The verification of the LHS is equal to RHS. If you are going to do with this kind of truth table, then that is going to be treated as the verification with perfect induction method. Similarly, the second equation of De Morgan's ones also we can see here. So this is A and B, once again the assigned variables 0 0, 0 1, 1 0 and 1 1. Similarly, in the last case, the truth table for complement values are also written here. A is 0, A bar is 1, A is 0, A bar is 1, and A is 1, complement of A at A is equal to 0, and A is 1, complement of A bar or complement value is equal to 0. So here B is 0, complement of B is 1, and B value is 1, complement value is 0, and B value is 0, complement of B is 1, and here B assigned value is 1, complement is 0. Now come back to this LHS value of the equation that is indicated with A dot B complement. So now A dot B means 0 0 are there in A and B. So 0 into 0 is 0, but complement value gives the result 1. Similarly, 1 into 0 is 0, that complement value is nothing but 1. Once again 1 into 0 is 0, but the complement value of that 0 is equal to 1. So 1 into 1 multiplication value, even though it is going to give the value 1, but since the complement is there, hence we are going to get the value is equal to 0. Similarly, if we are going to see the right hand side of the equation, so then A complement and B complement values are taken into account, and A bar plus B bar. If you are saying A bar plus B bar are 1 and 1, then automatically A 1 plus 1 is the result is 1, and 0 plus 1 the result is 1, and 0 plus 1 the result is 1 if both the values of this equation are assigned to 0 and 0 with the last row of this table, then automatically we are going to get A bar plus B bar is equal to 0. So similarly, this way of finding the values or equating the LHS equal to RHS is treated as perfect induction method. The next, proof for few Boolean algebra theorem. The first one is distributive law. So here we are having the equation A plus B into A plus C is, should have to prove it like A plus BC. So taking the LHS value A plus B into A plus C, then what we are going to do is simply we are going to multiply A into A is written here, A into C is written here, B into A is here, and B into C is here. After that, A into A is treated as A. With the previous slides discussion, it is possible for us to come to the conclusion A dot A is equal to A. Then we are going to take A as a common factor between these two. So then automatically A, if you are going to take out, then we can write these two like A into B plus C, and B C is taken as it is. Now it is going to become, if we are going to take A as common here once again between these two part of the equation, so then A is taken as common, in place it is 1 plus B plus C. If you are considering this B plus C as a simple single variable, then automatically 1 plus any variable value is going to become 1. That is depicted in the next line. So A into 1 plus BC as it is we have taken, hence finally we can come to the conclusion and we can write this A plus B into A plus C is equal to A plus BC. That is the required result or proof. Next, the absorption law. Here A dot A plus B is should be proved to as A. So now taking LHS, A dot A plus B is equal to, just once again we should have to multiply A into A is like this, and A into B we have taken here. So A into A is treated as A, and this AB as written as it is. Now what we can take is A, if you are going to take as common, then we can once again we can write like this, 1 plus B we are going to write, that is equal to 1, or this any one A plus any value is there. Already we have seen in the previous slides, A plus anything, okay, if it is there, then we can write it as A only. So therefore, so here the second equation what we can see here is A plus AB is equal to A. Taking LHS, A plus AB, if here already it is there the part, so the same part is continued here, A into, just if you are taking A as a common, we can say A into 1 plus B. So then 1 plus B can be rewritten as 1, and finally it can be concluded as equal to A. Next, A plus A bar dot B is equal to A plus B. Taking LHS value, so A dot 1, so we are here nothing is there, just we are going to add 1 multiplication value here, and remaining part as it is we are going to write. So now here the B variable is not available, hence we are going to write it is A, in place of 1 we can write it as 1 plus B, and as it is A bar dot B. So now A into 1 is A, and AB and A bar B. So here A is as it is, and in these two expressions, part of the expressions, B is taken common, then we can say B into A plus A bar. A plus A bar is always equal to 1, hence we can come to the conclusion A plus B into 1 is treated as simply A plus B, that is the required one as RHS. It is proved. The fourth one, AB plus BC plus B bar C, we should have to prove it AB plus C. So in this case, take once again the LHS value and start doing AB plus, if you are going to take the C as common, then C into B plus B bar, that B plus B bar can also be equated to 1 if any, okay, this complement, sum of the variable and its complement is always treated as 1 only, hence with that it is possible for us to write it as 1. So AB plus C into 1 can be rewritten as AB plus C, that is the required result, and the proof is completed. So now the logic gates. A logic gate is an electronic circuit which makes logical decisions. The most commonly used logic gates are NOT, OR, AND, NOR and NAND gates. In addition to these, XOR, XNOR gates are other types, and which can be constructed using the basic gates NOT, OR and AND. That is, XNOR and XOR gates can be constructed with the basic gates, that is NOT, OR and AND. First one is the NOT gate. The NOT gate performs the basic logic function called inversion or complementation. That's why the NOT gate is also called by the name inverter or inverting gate. So next one, the purpose of this gate is to convert one logic level into the opposite logic level. Means if 1 is there, that can be, it is going to convert it into 0, and 0 is there at the input, it is going to convert it into 1. It has one input and one output. That is shown in the table here. So, and also the symbolic representation indicates the, or it satisfies the last line, that is it has got only one input and only one output. So this particular symbol what we are writing here is exactly, it is a representation, symbolic representation of the NOT gate, and its truth table. A variable value is input, at the input is 0, the output is going to become the complement of that. That is represented with the equation here, that is called by the name Boolean expression for the output. So once again the input value is equal to 1, then complement of that can be written as 0. That's why A, this and Y values what we are indicating is nothing but the truth table for the written symbol NOT gate. And the OR gate. The OR gate performs logical addition known as OR operation. The OR gate has 2 or more inputs and 1 output. The output of OR gate is high, that is logical 1, only when any one of the input is high. The output is low, that is logical 0, when all the inputs are low. So the OR gate symbolic representation is given here, and in the second line what we are saying, the AND gate may be having a minimum of 2 or more than 2 inputs and only 1 output we are going to get. So here 2 with truth table is defined with 2 variables at the by considering at the input A and B. So the logical or Boolean expression for this y or the output can be written as A plus B. So in this, the first one, A and B are equal to 0 0, and if you are going to put A and B values in this expression of y, then 0 plus 0 becomes 0. Similarly, if A value is assigned as 0 and B value is 1, once again the input values, if you are going to put in this expression, then automatically 0 plus 1 becomes the 1, because it is an additional operation. So the next one, the A is equal to 1 and B is equal to 0, if what you are going to indicate at the input, then automatically this becomes 1 plus 0, the result is equal to 1. If both the values of inputs are 1 1, then also according to the Boolean mathematical algebra, so then what happens, 1 plus 1 is also treated as 1 only. The symbolic representation, truth table and the expression together we have written for OR gate in this. Next is AND gate. The AND gate performs the logical multiplication known as AND operation. The AND gate has 2 or more inputs and 1 output. Third point, the output of AND gate is high, that is logical 1, only when all the inputs are high. The output is low, that is logical 0, when any one of the input is high, input is low. So that is indicated in the table along with the expression, and this first part of this one is represented as a symbolic representation of AND gate. So next, if 2 variables assigned A and B are given here in the truth table and y is also given here. So in case A and B both are equal to 0, then if you are going to put the value 0 into 0 in this expression, 0 into 0 becomes 0. So similarly, if A and B values are 0 and 1, then 0 into 1 becomes 0. Next, if A value is equal to 1 and B value is treated as 0, then automatically that 1 into 0, if you are going to put in this equation, the outcome of this equation is looks to be 0. And only when A is equal to 1 and B is equal to 1, that is already we have said, that is 1 into 1, both are equal to high, then the output is going to remain high. So this is going to give an idea about the symbolic representation of the AND gate, and this is going to give the idea about its truth table, or how it is going to respond to the different values of the variables given at the input, and this is the mathematical expression what we are going to write for AND gate. Next is the NOR gate. Usually we are going to say the NOR gate is a combination of the 2 gates, that is, it is the NOR gate. If we are going to write the NOR gate, then first we are going to execute the operation of the OR gate. So OR gate can be written like this. So this is the variable 1 and this is the variable 2. So if you are considering A and B are the variables, then at this point, at the output of this, we can write A plus B. That A plus B combined together, if it is taken as the input to the NOT gate, then automatically the y value what we are going to get here is nothing but a plus b is the input value for this NOT gate, and that value is appearing with its complement value. So therefore what we can write, if a is and b's are treated, and y, if we are going to write here both a and b are 0 0 in the first line, if I am going to write it as a plus b, both a and b are 0, hence this is written like this. Therefore finally I can conclude a plus b total complement, okay, this value automatically this becomes 1. If a is equal to 0 and b is equal to 1, then a plus b value becomes 1 and the complement of that value becomes 0, and here 1, and if it is 0, once again the a plus b value becomes 1 and the output value becomes complement of this 1 is equal to 0, and both the values are 1 1, and even though the value of a plus b is equal to 1, but the complement of that a plus b, some value is going to become 0. Hence in the truth table of this we can see 0 0 is equal to 1. Finally we are going to write only these things. So only these three, so that y value 0 0 is equal to 1, and 0 1 is equal to 0, 1 0 is equal to 0, and last line both inputs are high, then the output is treated as 0. By combining these two diagrams we can write it as a single one just with a NOT representation at the output of this gate. So two inputs a and b with this kind of symbolic representation, y is nothing but a plus b complement value. This is represented as the NOR gate. This is the symbolic representation of the NOR gate. Now similarly it is also possible for us to deal with the NAND gate. So here this is the NAND gate. Once again here we are going to make the combination of AND followed by the NOT. So AND representation is already we know, so we are going to write the AND gate like this with two input values a and b, and that output is connected to the NOT gate. So a dot b here at the output of the AND gate, this is the AND function and this is the NOT function. So here whatever the output a and b is coming as multiplication value at the output of the AND gate, and that is going to be complemented, okay, this is a dot b looks to be complemented when it is passed through the NOT gate. Hence the a and b, if you are considering between this, we should have to consider this also. So then finally I can conclude the y is a complement of this a dot b. So if both are 0 0, then a dot b is also equal to 0 and complement of 0 is equal to 1, and any one value is 1, still the multiplication value becomes 0, hence the complement is 1, and 1 0 is also equal to 0, but the complement value of a dot b is equal to 1. If both are 1 1, the a dot b value becomes 1 and the complement of this 1 becomes 0. But while writing the truth table for the AND gate, we are interested only to write these three columns. So directly if you are going to write a NAND gate, that can be represented with a NOT at the output of this gate. So this is the final symbolic representation with the two variables a and b, and this is equal to a dot b complement. So this is the symbolic representation of a NAND gate. Now the same thing is also depicted in this slide. So NAND gate is shown, and the same to the table, and y is equal to a dot b complement is written. Next, exclusive OR gate. exclusive OR gate is a gate with 2 or more input and 1 output. The XOR gate operation is defined by a symbol representation like a circle with plus mark. So that is this symbolic representation we are going to write like this for whenever we are going to write the that is exclusive function, then it is indicated with such kind of a circle with within that circle plus mark. The output of XOR gate is low when all the inputs are identical, otherwise it is high. So with the equation, how it is possible for us to explain that, let us see. So the XOR gate can be represented with the equation. This is XOR gate. That XOR gate is represented with the equation A bar B plus A B bar. That is the equation. So this can also be represented as A with a plus mark, a circle exclusive operation, okay, indication, and with B. So now with the basic things, if I want to write, okay, another way of writing is this. So this line is having the variable A value. On this line we are going to take the B value. First, if we are going to take the A complement, then we are going to write a NOT gate here to make it A bar, and as it is we are going to take the B value from here, okay, and then it is going to be connected to the AND gate for the fulfillment of this is the AND function. So this is the AND gate. So this is one AND gate. So the AND gate value here A bar is there, and this is because A is input A bar and here B is there, hence the output of this is A bar B. Similarly, for this part of the equation we are going to put as it is the A, and B is taken through a NOT gate. So then we are going to have once again one AND gate here, okay, and that AND gate output is nothing but A is coming as it is, and whatever the B we are having here, it is complemented as B bar, hence this is A B bar. So these two outputs must be summed here, because summation of these two are summing, okay, that is sum operation is there to complete the sum operation of these two values, okay. So then we are going to write the OR representation. So this is the OR. Finally this OR output, what we are going to get is Y, that is equal to A bar B plus A B bar. So this can also be represented as A exclusive B. So this is the circuit diagram, but symbolically if we want to represent, then a single symbol can be written for this exclusive OR operation with two inputs A and B, and this is indicated as Y is equal to A exclusive B. This is the expression, or and this is the symbolic representation for XOR gate. Now we move to the next. This is the truth table and its expression, and lastly we can say that is exclusive NOR operation. So exclusive NOR operation we can say like this, very simple. The same diagram what we have given, that can be a little bit altered and it can be indicated. So first let us see the its function, how it is going to work. The exclusive or NOR gate. An XNOR gate is a gate with two or more inputs and one output. Secondly, the XNOR operation is defined by the symbolic representation, that is circle with that same thing, circle. This is exclusive OR operation can also be represented with like this. So the third one, the output of XNOR gate is high when all the inputs are identical, otherwise it is low. So here the circuit diagram of exclusive NOR gate is given. and logically, okay, how the circuit diagram can be represented is also, it is given here, that is a symbolic representation and along with the truth table, and this is the expression. So we will go back and we will see how to write this particular circuit, and this is, so now this XNOR gate, this is already there. So XNOR, simply by adding the n here, so if we are going to add n here, this becomes XNOR, then automatically one complement must be taken, and this must be also be complemented. Why means, the symbolically, if we are going to reproduce this like this, so this is an exclusive OR gate with A and B, two variable values at the input, and this is y is equal to A exclusive B. So now if we are going to connect a NOT gate to the output of this, then this function is looks to be complemented. So therefore final, okay, this is the final y can be rewritten as A exclusive B complement. So this is the way how to write. So then automatically whatever the OR gate truth table is there, that y value must be complemented and it should be represented. So exactly that looks to be opposite, means if both 0 zeros are there, then the earlier XOR gate value was equal to 0, but it is complemented here. So 0 plus 1, as per the XOR gate, it is equal to 1, because the 0 plus 1 is equal to 1, but it is complemented here, and this is 0 plus 1, it was earlier in the XOR gate it was 1, but because of the complementation it is going to become 0, and 1 1 is equal to, finally it is equal to 1. So this is the truth table for this, and the next we may move to universal gates. What is the universal gate? The NAND and NOR gates are termed as universal gates. So because any logic function can be built by suitably interconnecting NAND or NOR gates, means the any gate for that matter, the basic gates like NOT, OR and operations can be built alone with NAND gate or alone with NOR gates. So because of this reason, any logical circuit can be built if only NAND gates are available with us, and any logical circuit can be built if only NOR gates are there with us. So therefore these two gates are called by the name universal gates. This universal gate discussion we are going to take in more detail in the next session most probably, but for the basic thing what we can still we can discuss, and we can say here this universal gates are having a lot many applications. So now let us see the universal gate. OR operation, NOT operation, and also AND operation with only NAND. These operations only with NAND. So now NAND operation, this is NOT equation is y is equal to, okay, that is A complement value if A is equal to 0, that is A is equal to 0, then y is equal to 1. If A is equal to, this is 1 and this is 2, if A is equal to 0, so A is equal to 1, then y is equal to 0. So then this can be rewritten like this in the with the help of this NAND gate. If we are going to take these two common, then automatically if you are writing this A, here also we are going to get A, here also we are going to get A, and finally the y is looking like A dot A complement. So here A dot A can be rewritten as A with its complement value. Hence this particular symbolic representation with short circuited two terminations at the input. Here two terminations are there, both the terminations are shorted, and a common input A is if you are going to give, then the output value Y of a NAND gate with this kind of setup is capable of giving the complement value. Then for example, if we are going to consider the AND operation is nothing but Y is equal to A dot B. Now if you are going to complement this Y value then double time, then the value is unaltered. Therefore this can be rewritten with the help of De Morgan's theorem like A complement dot B complement, that is plus B complement, and finally you can write like this. So further, if you are going to A double complement dot B double complement, and this can be rewritten as double complement of A is A and dot as it is, and double complement of B. So it has come back to its original value. But while writing, I am going to split this equation. While writing the AND gate with the only NAND gates, we are going to rewrite this equation, and we are going to conclude like this: Y is equal to A dot B complement, okay, then the another complement we are going to write here. So the first one is, first if you are going to write the NAND gate with the two variables like this, so A and B are two variables, the first point is A dot B complement we are going to get, because AND operation is A dot B followed by not is complement. So further if you are going to write this first gate, then automatically you are going to get the value, this is thing. So in both the terminations A dot B is applied here, and also A dot B complement is applied here. Simultaneously the same thing is applied here. So therefore A dot B, this is the applied one, and when it is observed as a Y, then it is going to be complemented once again. So Y is equal to A dot complement of complement. Hence that is nothing but the execution of AND operation, because already we have shown AND operation, we have already solved this and we have shown it. Once again it is coming back to the same value, Y is equal to A dot B. Hence the AND operation can be executed. This is AND operation, but in this case both the gates are NAND gates. By using two NAND gates, it is possible for us to execute the AND operation. Similarly, we can execute the OR operation also. So next we are going to take this universal gate discussion in detail, and by this I am going to conclude my session here itself. Thank you.